Yeah, so what we can do today is have a quick review of the generative modeling part that we're going to implement today. And then we can go through the second tutorial. But maybe if you have questions about the first one, we can do it now. If there's anything you're like, okay, that didn't make any sense. You've probably forgotten about what didn't make sense from these many days. I'm sure you'll feel it quickly as we come back to it. But also, as I said the other time, if there's something that you'd like to work on related to like ML and generative models, we can also do that today. And yeah, feel free to ask any questions. But in terms of the tutorials, let's see if this works. So this is the second tutorial on generative models. And the idea is to use the same data set that we used last time. But in terms of classifying, what we're going to be doing is generating. So we're going to build a generative model on that data set. And we're going to be using flow matching because the simplest implementation. So we'll refresh a bit what flow matching is. But you can see that the main idea is to get to something that can generate numbers, right? So that you can sample from white noise distribution and turn it into a number, right? First, unconditionally, so you can sample any number. But then we can also look into how do you make it actually conditional. So I can say I want to sample a 7 or a 5 and not just any number. Right, but that would be like the goal of this tutorial. But okay, let's refresh a bit what flow matching was. So this is the schematic that I was showing you the other day on general generative modeling, right? Where you have a base distribution that is kind of simple. So you can sample from it, but also evaluate probabilities. Usually a Gaussian, but it doesn't have to be. But it usually is a Gaussian. And then you have your data distribution. Yeah.
Would it be okay sort of to back up a little more and go to the generative and the discriminative, sort of like a different,
sure. Yeah.
That would be helpful. I think that's just one step before that, just to.
Yeah, that sounds great.
Sorry about that.
Yeah, no, that's great. Please, yeah, interrupt anytime. Very happy to go back. Yeah, so last week we were working on the discriminative aspect, right? So I have label data, so I have pairs of X's and Y's, and I want to basically draw lines that separate them maximally, right? So I'm going to learn a transformation of my data that put them in a space where they're very separable. That's basically what the neural network is doing, right? Now, in the generative case, I don't have label data necessarily. So I only have images, for instance. So I have X's, but I don't necessarily have Y's. So I can learn the distribution of P of X, like the probability of my data. And I can sample from it, but I can also evaluate densities, which in science can be very, very useful, right? Like likelihoods. Now, I may also have labels. So I may have pairs of X's and Y's. Like in this case, I know what images come from cats, which ones come from dogs. And then I can train a conditional generative model, P of X given Y, right? But I may not have that, right? I may only have P of X.
Okay, I just have one more question about that approach. So basically, I mean, the input for the discriminative approach is basically you have like either the cat or dog, and then you try to identify it. So X would be either cat or dog, and Y would then be sort of like the probability that it's basically it's a dog, and that's right. The discriminative approach. But when you do the opposite, you'll basically input that it's a cat or a dog, and then you generate an image which should look like that one. Is that sort of like the
exactly? That would be the conditional one, right? P of X given Y. In the above model, the P of X, you wouldn't input anything. You'd be like, just generate images that look like my data distribution.
Mm-hmm. Yeah.
So it could be human faces, right? Just generate human faces, no conditioning. But in the cats and dogs example, you may have the conditioning, right? So then you can say, I want dogs, and it will generate dogs. Or like when you prompt with text, it's because it's being trained conditionally like that, right? P of X given Y. You shouldn't, and it's very simple. You can use captions, right? Go through the internet, take every caption that an image has, and just align them there. So that's what they're doing. But yeah, as we said, there's actually a relation between the two, right? Through Bayes' theorem. So the generative and the discriminative approach are actually related. And you can use a generative model as a discriminative model as well by using Bayes' theorem, right? So I can compute P of Y given X using P of X given Y. And these tend to be more robust because the generative model has to learn to generate the image, right? Whereas the discriminative model can cheat very easily. So if you're looking for cows and you see grass, it'd be, oh, grass is a cow. Whereas the generative model has to actually make the shape of the cow, right? So it can't cheat that easily. So it tends to be more robust, but obviously they're way more expensive, right? Because you have to learn to generate images, which is a much harder problem than discriminative problems. So you may need like larger data sets, etc.
I mean, in the case of your galaxy distribution, it means that that would be your input, and then the sort of the model actually would generate several instances of other galaxies.
Exactly. That are from the same distribution, but look different to your training set. In the ideal case, right? The non-ideal case is just generating the same images as your training set, right? So it doesn't have a diverse. Your PDF is completely like overfitted as delta functions of your training set. That can happen if you have a very small training set. But ideally, that's not what's happening.
Right.
Yeah. Any other questions about generative versus discriminative? Let's go. Right, and then we talked a bit about, what it looks like in practice, right? So you have a parametric PDF that has some free parameters that are going to be the weights of your neural network. And your data, the parameters that we want to optimize, and the loss function tends to be maximize the likelihood of the data, but not always. So actually the model will implement, that's not the loss function. Because, we can go through why that was the case. So the type of models that we're going to be talking about are related to continuous time normalizing flows. So this is why we're showing you the other time, right? Where we're going to parameterize x as a function of time. Time goes from 0 to 1. So it's fictional time, right? To go from our base distribution to our data distribution. So at time 0, we're going to be in a very simple distribution, usually a Gaussian, but again, it doesn't have to be. At time equal 1, we're going to be at our data distribution. So in this video, you can see how it actually looks like, right? So you're learning a velocity field that takes you from a Gaussian distribution into your data distribution. So this is the PDF, right? One-dimensional example. So in this case, we know we have this ODE for sampling, right? So we learn a velocity field that allows us to sample, and it's invertible. I can go from 0 to 1 or from 1 to 0 by just inversing the numbers here, right? In the interval. And I can compute P of x by solving this ODE as well. Now, this is very, very slow. So if I wanted to train my model with maximum likelihood, it'd be really painful because I have to solve this interval. It's doable, but with high resolution images, it becomes impossible and very painful. So that's why continuous time normalizing flows are not the model you've heard about, most likely, right? Because although they're very neat, I think it's a very simple and nice idea of how to get to an invertible transformation, right? By just writing it as an integral. Yeah, in practice, it's just not very practical. So that's why our loss is not going to be maximum likelihood. Our loss is going to be regress the velocity field. So we're going to assume we know the path. So, okay, this is continuous time normalizing flows. This is expensive. So what we're going to do is we're going to assume that there is an interpolant between our base distribution and our data distribution. And this could be anything. We pick linear because it's simpler, right? But you could pick anything. Now, this is how it looks like, right? So you have some base distribution in 2D, x naught, like a Gaussian, and you want to sample from this data distribution that is 2 Gaussians. So linearly, it's going to look like this, right? From 0 to 1, some samples will move to this mode, some samples will move to this other mode, just linearly. Now, if I wanted to compute the velocity field marginalized over x1, because when I sample, I don't know where I'm going, right? I'm at x0, but I don't know where x1 is. x1 doesn't exist yet, right? I want to sample x1. So I would want to marginalize over all the x1s in my training set. I will need to do something like this. So I know this conditional velocity field because I know the interpolant if I know x1, but I don't know the unconditional velocity field, which is the one that I need for sampling. So how do I do regression? So what you can do is say, okay, I want to match. So I have a neural network that doesn't know x1. So it only knows xt at a given time, but it doesn't know the endpoint. I want to predict the conditional velocity field. Because at training time, I do know x1. I just don't know it at inference time, at sampling time. And it turns out that the gradient of this loss function is the same one that we were after. that will include this marginalized velocity field. So it is a very handy trick, right? And this happens very often in machine learning, that you can't optimize what you wanted, but the gradients are the same as the ones that you wanted. So that's very, very useful, right? Because they're pointing in the right direction, and that's all you care about. The value of the loss will be different, but the gradient with respect to the model parameters is the same. So it's all good.
What is conditional about?
This conditional ut of x given x1. That's what I mean by conditional.
Oh, I see.
So maybe I can draw something. In that example where we had a 2D distribution, right? This is our x naught. So I use a Gaussian unit, like a normal distribution. And now we linearly go to our data distribution that has 2 modes. So this is x1. Okay, if I have a new point outside of my training set, I say, now I want to sample a new x1. My velocity field was, well, my interpolant is xt is tx naught plus 1 minus tx1. But I don't know x1. I want to sample x1. So what do I do? There's nothing I can do, right? And the velocity field, so I know the velocity field, vt of xt given x1, right? I need x1 to compute my velocity field. I don't have x1, so I'm done, right? There's nothing I can do. I'm stuck. So I didn't gain anything by assuming this, because at training, inference time, I don't know where I'm going.
Yeah.
So if I wanted to learn, like, marginalize over all possible x1s, so if I marginalize over all possible x1s, you will have to solve this interval that becomes intractable. Like, yeah, you can't actually solve it. But you can learn a neural network that won't be given x1. So the neural network will only see xt. So then your velocity field will lose this dependency. So now I can estimate it, right? At any time by changing xt. So I can solve the ODE, right? Because I'll start from x0. I know how to sample from x0, because it's just a Gaussian. And now I'll compute v of x0. And I'll go to the next step. And now v of x 0.1, v of x 0.2, etc. And I'll keep moving without knowing where I'm going, right? Whereas before I couldn't do that.
Okay.
So that's the difference between conditional and unconditional.
So in one case you know the endpoint basically.
Right.
In the other case you just know the local conditions.
Exactly.
And you progress from this.
Exactly, yeah. So I want to, my neural network can't know where I'm going because I don't know where I'm going. But at training time, I can take advantage of the fact that I do know where I'm going, right? So that's what we're doing here in this loss function. So this is the neural network. So it only knows the local time. And this is the true answer that knows about the endpoint as well.
So I have a question about the condition that you impose on this inference. So here you use x1, which is basically the end state of the distribution as the condition, but can it also be something else? For example, some other physical properties that you are associating with the galaxy instead of the one that you're directly trying to predict out of this neural network. For example, when you are predicting galaxy star formation rates, can you use, say, galaxy mass as a condition?
Yeah, totally. Yeah. Okay. So this is an unconditional model. So you just want to learn p of x, right?
Right.
But if you wanted to learn p of x given y, which is what you're referring to, right?
Yeah.
It would just, this velocity field just needs to know about y.
Sure.
So that's the only difference.
Yeah, but I guess the more variables that you're trying to condition this neural network on, I guess the more complicated the structure will be.
Well, actually, the simpler it gets, right? Because the more you know about the conditioning, the simpler the generative model becomes, right? Because there is less that it has to
Less structure,
right?
Okay, yeah.
If you have if this is my overall space of all galaxies,
yeah,
I have to learn how to move over all the space. But if I now section it into different properties, wise, right? Then all these become simpler actually, because you know more about your system.
right. But still, you're I guess what I'm trying to get at is but you have to account for all the different possibilities in the y variables
Yeah.
here, right?
Yeah.
So maybe okay, so with a specified, say, a parameter set in the y vector, you probably are slicing your parameter space down to
Right.
shrink the I guess the potential size of your prediction space.
Or your data manifold, right? Of your
Right.
manifold.
Yeah, but still you're not changing the whole manifold. I mean,
No, because it's still combinations of them, right?
Right, yeah,
But you are making this mapping simpler. Because now you are inputting this, right? So
Sure,
the mapping
yeah.
is actually simpler. Whereas in the other case, you have to marginalize over that, right? And all
Right,
has to
yeah,
learn to do
yeah.
this,
yeah.
which is not necessarily easy, right?
So, okay, so I guess another follow-up question would be, when you are training, for example, if you have trained a neural network to capture the conditional probability distribution of P of X given Y, then after you've done the training, is there any way to, say, marginalize it over Y to get the unconditional distribution? Okay,
You could, but it tends to be very hard, right? Because if Y is high dimensional, these integrals, you have to Monte Carlo it, right? Like it's gonna be so painful that you're better
Oh, yeah.
off training a separate model that just gives you P of X.
okay, so it's not so advertisable compared to,
It depends on your Y dimensions, right? The dimensionality of Y.
yeah, okay,
If Y is high dimensionality, then
sure, yeah, okay,
the integral is just
Yeah.
so much.
Yeah.
But if it's low dimensions, then yeah.
okay.
I mean, training one model is very easy, right? So it's gonna be easier than solving that integral 99% of it all the times, right?
Okay.
Any other questions about it?
Yeah, I have a question about VTX0. I'm not quite sure where do you get that from? So like the starting condition, basically the starting velocity.
Right, so X0, I assume, is a normal distribution, right? So sample from a normal with mean 0 standard deviation 1. So I can always sample from it, right? This I know how to sample. So now I can always evaluate the f X0, okay? So this is my neural network that I'm gonna learn. So the neural network that I'm learning, so the loss function that is there, right, is I want to estimate the expectation value over T, X0, and X1 of V. So this is my neural network, right? So it has some free parameters. It takes X of T and T, and it computes the actual velocity. Okay. So this is the mean square error compared to the actual velocity. Now the actual velocity is very simple because I assume a linear interpolate. So it's actually just going to be X1 minus X, not X1 minus X0, right? So that's very simple. I could assume something else, yeah, that's fine. You just have to take the derivative, right, to get to
Right,
the
yeah.
velocity.
Yeah. But you only know that at during
Training. You only know this during training. But you're making sure that your model doesn't know anything about X1. So your model only gets XT and T.
Yes.
Now we have to solve the expectation value, right? Because now usually on a loss function, you have something like expectation value, like the average, right, of your data set, let's say X. So in the discriminative example that we had before, we were averaging the cross entropy, the binary entropy, over X and Y, right? So we're getting batches from our data set and taking means. So the expectation value was only over the training set. Now we also have this expectation value over T, right? In theory, then for each X0 and X1, you will sample many T's, right? Now things become expensive, so you don't necessarily want to do that. What we do in practice, and it works very well, is when you sample your batch of examples, right, of X1s, you also sample the same number of X0s and the same number of T's between 0 and 1. So for each batch, you get a set of examples, so you'll get a set of images, for instance, and you will sample a set of X0 and a set of T's of the same size. So what the model is seeing at any given time, so I think I had
Assuming X0 is Gaussian.
X0, yeah. So X1 is your data.
Right.
So if we look at this image there, right? So you see At time 0 is just Gaussian, white noise, right? At time 1 is my, let me move this. Oh, it's not me.
Oh, what happened?
It's all right, I guess.
Oh.
But what you can see, that's an 8 already, right? So only the last box is missing there. Yeah, here you have white noise, right? And here you have your data distribution, next one. Now, at training time, we're going to be sampling different X1s, so different images. And for each one, we'll get a random time. So maybe this one, you'll get this one. So obviously, it's very difficult to predict the velocity field from here, because this looks like white noise, right? It's much easier to predict it from here. But you get an average over all these times. So at training time, you're going to be training it on different T's. For each image, on a different T, just to solve that expectation value. Just a handy way of solving the expectation value, right? Otherwise, for each image, you'll have to sample different times, average. It'd be annoying, right?
So just to build some intuition into this training process, so are you effectively saying that when for samples that actually have a larger t-value closer to 1, your predicted, or like at least in the process of the training, your predicted velocity field would have smaller scatters as you approach to, say, the end state?
That's right.
Okay.
Yeah, it's so much harder to predict it from here, right?
Yeah.
Because there's no signal there. But because at training time, you're given different times, like from here, it's already pretty obvious, right?
Yeah.
It really looks like an 8. You can see here in the code, this is your the velocity model that you're learning, so your velocity field, which is a neural network, right? And you see that the input is x at time t and t. So it's not x1, right? x1 is not an input. Like your data is not an input directly.
And training time?
At training time. So this is the loss function.
Oh, I thought at training time you actually would know your S1.
Well, you know it so that you know xt.
Yeah.
Well, the loss function does know it. The velocity model that doesn't, right? So this is the loss function. The loss function knows x1, right? It's a function of x1. Okay, so the loss is a function of x0 and x1. It's not a function of t because you're averaging, right?
Yeah.
But the velocity field doesn't know about x1.
Oh, okay. The velocity, okay.
So this is the same thing that we were discussing last week, right? The loss function gets thrown away after training, right? The loss function is just an excuse to learn.
Right.
But then the model is all that matters, right? You're not going to use the loss function for anything else, only to learn the weights.
So basically you phi would be the parameters.
Yes.
And basically you only use the loss function to determine phi, and then after that span you throw away the.
Yeah. Then you can just solve the ODE, right?
Yeah.
And you know that d of xt dt is the velocity field. So I can integrate from 0 to 1, start sampling from my Gaussian distribution, and get a sample from my data distribution. In a deterministic way, right? So this is an ODE.
But that will also explain how you got x v0 basically.
Right.
Because I mean, when you know v phi,
Okay.
and then you just put it in x0, then you get the initial velocity as well.
Exactly. And then you keep integrating, right?
Right,
Like
exactly,
the
yeah.
next point, and yeah,
Okay,
iteratively solve the ODE.
thanks.
Yeah, it's not an easy concept, so yeah, it takes some time to sink in. Any other questions before we start? Maybe it's a good time to go back to the differences between generative models as well before we focus on flow matching. Because yeah, you probably heard of diffusion models and other stuff, right? Normalizing flows. And it might get a bit confusing. So in this slide, I was trying to highlight what the difference is, right? So you're always trying to do something like this. So bridging two distributions in some way. So you always need some sampling from a base distribution that you know how to sample from, which is usually a Gaussian, but not always. And you're going to bridge it to your data distribution, but you can do it in different ways. So one question is whether this bridge is deterministic, like the one we have, which is an ODE, or if it's stochastic, which is an SD, right? So diffusion models build an stochastic bridge. So you're always sampling some noise, right? Whereas flow matching or normalizing flows have a deterministic one, right? So flows tend to have a deterministic one. Now, depending on your problem, that might matter or it might not matter. Most of the time, it doesn't matter. But sometimes people say that if you have an stochastic one, you may be able to correct errors. So let's say I start from here and I get the velocity field wrong. So I go completely off. Whereas in diffusion, you might first predict it wrong, but because you add some noise, you might still end up randomly in the right place. But yeah, I think it's not a big deal in practice. But it's one of the differences. Then another difference is whether P of x naught is restricted. So I told you most of the time is a Gaussian. And for diffusion models, it's always a Gaussian. So diffusion models are built on Gaussian distributions. Whereas in flows, it doesn't matter. X naught could be any distribution, which sometimes is very useful, right? In astrophysics, sometimes you have a very good low resolution model, like effective field theory of what's happening on large scales, but you're missing the high frequency details, right, of a simulation, for instance. So you might want to start from that low resolution picture to get to your high resolution picture, because they're already very close, right? And with flow models, you could do that. With diffusion models, you couldn't. You have to start from a Gaussian distribution. You can condition on it, but the model will learn something very complex. So oftentimes it's actually very useful to start from something that is not a Gaussian.
Can I just ask, what would be the analog? I mean, effective field theory, basically, when you go to the UV, you basically would use the energy as your parameter, basically, and that would kind of be the flow. And the question, what would be in the diffusion model?
Well, I'm thinking more of, let's say that I have, in cosmology, if I have a large scale structure of the universe, I can use linear theory to get something that looks like very close, but very smoothed out, right? I'm losing all the like high frequency details, right? So I could take my linear theory as my x naught, because I can sample from it very easily, and x1 would be my high resolution simulation. But in diffusion, I could condition on linear theory, but I will have to start from white noise, from something like that looks like what I was showing you earlier, right? Completely white noise. So the mapping from white noise to the high resolution simulation is very complex, whereas the mapping from linear theory to the high resolution simulation is much simpler. So you'll need a much smaller number of simulations. The mapping might be more interpretable. Like there's many advantages to doing that. When you already have a theory that gets close, but not quite there, you can like learn a correction on it.
And that would be the case, I mean, going from a linear theory basically to nonlinear with like clustering and so. I mean, that basically, and that would be the flow.
Right, the flow will do that, yes.
Yeah, and but wouldn't you also start from a linear model in with diffusion, or would? No,
you would start from a Gaussian distribution. You would condition on the linear model, but the mapping is from x0 to x1, right? So what matters is, so you're learning a mapping. Let's say that you're doing p of x given y, based on going from x0 to x1, right? So in this example, y in the diffusion model, y could be your linear theory prediction, but x0 will be a Gaussian distribution. Whereas in flows, y could be your linear theory, but x0 could also be your linear theory. So the mapping becomes. So it's subtle, but actually in practice it's very important, right? Because it's what the model is mapping from x0 to x1 with the help of the conditioning, but still it has to learn to move all the pixels. You think about all the pixels that need to be changed, it's a lot of them. Whereas in the case of linear theory to nonlinear, it only needs to locally change things, right? So you don't need a model that needs to know what's happening in the other side of the image. You only need to know what's happening around. So it can be a much smaller model, more efficient. In practice, you probably can get both to work if you have enough data, but you probably shouldn't.
So I have a question about the startups of this flow matching. So when you're trying to generate a distribution using the trained machine learning model, you start with a Gaussian distribution. I'm wondering is there anything that we can learn about physics from this starting distribution?
Well, there's some fun things you can do. So in particular for these ODE models, this is perfectly invertible, right?
Right.
So you can go back.
Yeah.
So one thing you can do is that if I train my model on simulations and then I use actual observations and I take them back, will it look like a Gaussian distribution?
Okay.
It won't, if it's out of distribution, right? So you can do things like that. But the best use is the fact that you can actually compute P of X, right? Because you know P of X not.
I'm sorry, what is the, okay, so. Okay, I would be puzzled by, what's the difference between the P of X versus P of X naught now?
Right. So you need a Jacobian, right? So this is what we had.
Okay.
Right. So, well, yeah, right. So Z here is X naught, right? So P of X is P of X naught plus this Jacobian term.
Right, so you're saying that this X is probably somewhere in between the initial and the end state of your,
Well, X is the end state. So let's say I give you
so
an image
X is the
of
end
the galaxy and I want to compute how likely is that image, right?
Yeah.
I want to get a probability value for a particular image.
Yeah.
Then I would take it back to X naught, compute P of X naught, which is a Gaussian, so I know how to compute it, right?
right,
And then I also need to solve this integral. So it's not true that P of X is P of X naught.
sure, yeah.
There's still a
Yeah.
contribution from your velocity field.
Sure.
Because things have morphed.
Right, I thought by X you were talking about X naught, but okay,
Right.
never mind. So.
So things you can do with X naught is use it to compute probabilities,
Yes.
use it to assess kind of distribution things are. But I think that's about it.
So you don't necessarily, well, and also because by doing this invertible transformation, you are preserving the dimensionality of the problem. And
Yeah.
you're not, I guess, without incorporating representation learning some way, you cannot just figure out what's the Latent space.
No, that's right. Yeah, X naught always has the same dimensionality as X1. Always. Which is different to a VAE, right? Where you always try to compress fast. And the other difference between models is how do you constrain this bridge, right? So what constraints do you set in this bridge? So normalizing flows, you're assuming that the bridge has to be invertible. So the function that you're using to go from base to data distribution from X0 to X1 has to be invertible, which is a super strong constraint, right? It's very hard to come up with machine learning architectures that are invertible. And we talked about one of them, mass autoregressive flows. There's others, but they're not the most flexible, right? So for a particular data set type, you always have to come up with a way to make it invertible. So that's why they're not very popular for like high dimensional problems, because it's very hard to come up with vertical neural networks. Now in diffusion models, the constraint is that the path forwards from X0 to X1 is going to be from X1 to X0 is add Gaussian noise. So you're going to be noising your data until you remove all the information and you only land with Gaussian noise. This constraint. In flow matching, we're assuming we know the interpolate. We're assuming some interpolate, right? So we're assuming this is the path that we're going to take. A linear one or whatever it is that we find simplest, right? So there's always some constraint on the path. It's not fully unconstrained, right? Because otherwise, nothing can land. Yeah.
Just ask about the initial distribution. I mean, in a way, I mean, when you have the normalized flow, you define the initial positions, whereas with the diffusion model, you basically sample the initial positions from Gaussian, from knowledge diffusion, basically.
Right.
Is that how you get the? I'm not 100% sure whether I are really correct. I mean, that's not correct.
Yeah. So if what you're trying to say is that X0 in flows is not constrained to be a Gaussian distribution, it could be anything. That's right. Whereas in a diffusion model, you're always noising your data into a Gaussian distribution.
on the way back, or.
Right, on the way from the data to, from X1 to X0.
Yeah, exactly. But, I mean, yeah, I'm a bit confused about X naught. I mean, how I get X naught, or how X naught differs in both models.
Well, it doesn't differ in a way, right? Like, it's just you have more flexibility in flow models. Flow models, X0 could be as skewed. I don't know, if I knew that my model has 2 modes, I would start with 2 modes, right? So my X0 is matching to X1 with 2 modes, right?
Okay.
So the model doesn't have to split. So for instance, for points here, the model would be very hard to learn how to split things into 2, right? So if I know something about my data, I could change X0 to reflect that. Whereas I can't do that in a diffusion model.
Yeah, I think that was it.
So it seems to me that you can choose different interpolants for
Yeah.
the whole process. So let's say I only care about the ability of the model to generate the end state distribution based on the input distribution. Then how would the choice of those interpolants affect this functionality, or?
Yeah, that's always a question. Same with diffusion models. In diffusion models, you're adding noise, but you're adding noise in particular ways. So you might add more noise at first, less noise. So this was called the noise scheduler. That is the interpolant, basically. So diffusion model is a flow model with certain constraints. So you always have some sort of choice on how do you do things as a function of time. You have all that freedom, right? So what people have found is that it doesn't seem to make a huge difference. So you have enough data, like the interpolant. So if you change this for like exponential interpolants or other things, there's small differences, but it's not like a huge deal. Or people wonder because, let's say that I'm going from flowers into animals, right? So my interpolant is, wow, that's a flower. Okay, flower. Into animals. That's an animal. Clearly. So if you do a linear interpolation, the in-between looks extremely weird, right? It looks like it looks like a blending of 2 images.
Yeah.
It doesn't look like something in between, right? So people wonder whether you could build interpolants that actually look like the in-between of those 2 things, right? And whether that will actually make better models. But so far, no.
Okay.
So far, the blending is fine. But I think it's interesting questions, right? Like, because yeah, for us, interpolating between 2 doesn't mean blending the 2, right? It means creating a new object. Right, slowly, right?
Yeah.
You would imagine some, but that's not what this is doing. So could you learn an interpolant that actually does that? But it hasn't, people haven't been very successful on that front. I mean, this is all very new, right? So I'm sure next year we'll be talking about something else. But it's all part of the same flavor, right? Like, they're not that different. That's what I was trying to say with this slide, that the mindset is always the same. It's just small tweaks to make the training more efficient. And maybe give you some more extra flexibility, like I want to sample from X0 differently. Or things where people, I think, found issues with normalizing flows is if you want your transformation to preserve certain symmetries. Like in chemistry, you want to sample molecules. Now, if I rotate my X0, maybe I want my X1 to rotate in the same way, okay? Or I want P of X to be invariant to rotation. So if I rotate my molecule, P of X shouldn't change. It's the same molecule, right? But in an arbitrary model, that will actually not be true. P of X will be changing as you rotate your molecule. However, in this kind of flow matching model, if my velocity model preserves those symmetries, P of X will also preserve those symmetries. So if my velocity model is equivariant, meaning if I rotate my input, my output rotates in exactly the same way, my P of X model will be invariant to rotation. So that extra flexibility has been very helpful to build more efficient models with smaller data sets, etc. So it's small tweaks, but they have a big impact on the practicality of generative models. But for small data sets and simple data sets, you won't see a difference between all these models. They all do very well. It's just when you get to more interesting domains that you start seeing the differences between them. But the general framework is always the same. So it's still useful to learn about them in detail, right? Because I don't think the general framework is going to change that much. It's just tweaks will come. Any other questions? Cool. So we can have a look at the tutorial. So it should be on the same repo as last time. This from 0 to generative JAX tutorial is number 2. And you should see that it has very similar language and setup. So it's also using JAX and the same data set MNIST. But now we're going to change from classification to generative models. Yeah, whenever you have a question, just feel free to raise your hand.
So I was trying to understand, and you may have gone over this already, so give me. So it's when people use these flows with simulation-based inputs, and they get posteriors, say on cosmological quantities, does the input matter? So if you went back to diffusion models and you're forcing the distribution to be Gaussian for X1.
Yeah.
If X1, you have freedom to effectively constrain it by your large scale structure distribution as you demonstrated up there or something like that. How does that affect the resulting posterior distribution? I mean, do you have to worry that things are going to get biased and
Right. So in simulation-based inference, usually by using a normalizing flow, but you still start from a Gaussian distribution. So you usually try to
assume? Okay, go ahead. Sorry.
theta given X.
Right.
Right. And usually you're doing normalizing flow that starts from, well, let's draw it as a distribution. From X naught, which is a Gaussian. So it's usually always a Gaussian. And now you're going to map it into your posterior distribution. So, okay, maybe we should call it theta naught. Okay, to not get confused. Now it's theta naught, because we're sampling our theta, right? And you're turning it into your posterior distribution, that might be multimodal, whatever it is, right? Theta 1. But this is a Gaussian. Now you're conditioning this mapping, so f of theta naught on X. So X is entering the conditioning, but you're sampling our theta in simulation-based inference.
Okay.
So simulation-based inference is generative models for thetas instead of for X's. So it's posterior models usually. You can learn the likelihood as well. Like you can learn P of X given theta. And this is actually way more robust. Like these models are extremely more robust. So you have to be very careful with these models. I think it's usually better to learn this. Now, the problem, why don't people learn this if it's bad? Well, because this is, the dimensionality of theta is much lower than the dimensionality of X. Because these are usually simple physical theories, right? They have a handful of parameters, theta, whereas X will be very high dimensional, be millions of galaxies, right? So that way, yeah, it's more convenient to learn this, but it's actually, I think, we're not gonna get robust cosmological constraints from theory model like this. It's not really happening. Because small change, you're learning this mapping directly on theta space, right, as a function of X. This can be very complex. Whereas here, at least, you're inputting the data and comparing it to your simulations on the data space, right? Non-linear transformation in X of theta.
It's certainly easier.
Yeah. It's just the dimensionality becomes worse.
Yeah, so it's the imbalance in the dimensionality between X and theta.
Okay.
This.
Well, because people insist in normalizing flows, right? Because if you use other models that work better for higher dimensional, so the point is that normalizing flows don't scale well to a higher number of dimensions. So if you try to learn the likelihood with a normalizing flow, it probably won't work. Right, you could use something else, right, that scales better, and then that will work.
That's really interesting. Thank you.
But you need a GPU to complete.
Well,
Because you just told me that I don't have a GPU.
right, so the first half you can do with CPU,
Mhm.
but the generative model will be rubbish. So you can generate rubbish.
Okay,
But I would start with the CPU because Colab only gives you like a limited number of free GPU hours, like I've already run out. So I would start with the CPU, make sure everything's working so that you get past all the assets like left in between, right? And things are running and you see a loss going down. And after that, I would try it on a GPU.
okay. So you can use a GPU from Colab? I mean,
Yeah.
because,
Yeah, if you go, let me share. You can also like buy credits if you want to. Right, if I go to the Colab. Yeah, you can change runtime type. And you can pick, but you see them, they kick me out of everything. Let me use anything.
but
Purchase additional compute units. But if you try, you should see that you can, well,
Yeah.
actually,
you
these
can
are not
use
too
it,
bad.
yeah.
You can try these ones,
Oh.
but you can probably access some of these as well, hopefully. But otherwise, it's meant to be running on CPUs as well, so don't worry too much about it. But if you want to get to generate nice numbers that actually look like numbers, then I'd be very surprised if you can do that on a CPU. Like you can, that'd be cool. So do try. They say that the hope for academia is that we're very good at doing things with little resources. So that can drive more innovation, the fact that we don't have resources. Not sure it's true, but
Just like DeepSeek.
right, exactly. But we can't be open AI. Sad.
I understand. This is one of the diffusion. If we didn't start with one, we would start with something that somehow it's a set of numbers, something that we set, but we would call that more than just a constraint because you have calcium.
Exactly.
Okay.
So in flows, you don't have that constraint.
Right.
It's that for those.
Right.
In diffusion models, what you would usually do, if you still want to use that information, it's like, I'll do this to then you make then Y can be your lower S.
Okay.
But actually, in this kind of flow models, like in problem of sample definitions for technology.
Yeah.
So you could general to do isomers, finals. Start from a feature model, right? So with like noise turning into visual visions, okay? Or you could do flow matching, right? So because what I was saying, right, so you flow matching and then it would look like flow magnetite, right? But this here, so it starts from the final and it kind of goes smoothly back to the initial. Whereas in the other case, what you see is, yeah, Gaussian noise turning into,
Right.
I think I have it.
That's right.
Because it's computational memory, trying to sample the answers, right? But it sees the progression block for a long time. And then more things like that, so it's but it really is a Gaussian block of that. Okay. So you can see it's this is a conformation function, right? Function carries those complex data. The block is so it's
Right.
find this thing. But now it starts to get the last thing. And then of course it's not together. But it sounds like Gaussian, right? Whereas in the other case, it's actually some from the animation, it's not one thing to issues, right? So this is a much more complex mapping than the other one. So you start with Gaussian block.
Yeah.
Whereas you really have to be a partner. Yeah. So for instance, if you have some fallacy, you have some low resolution intensity field, it's possible mesh, let's say it's 1 second. Possible sample it and get a very good size. So you need to correct that. Which is not.
Right. Thank you. Yeah, that makes a lot of sense. So.
So basically, I download all the. Which is. And sort of like, if I understand correctly, the image that we have.
Yeah.
So that means that's the number of pixels you will have.
Yeah.
And that's basically your initial distribution. That would be like the points.
The dimensional of the initial distribution, yeah.
Yeah, I mean, that would be typically like the initial galaxy factor.
Right, so X1, it'll be X1.
It would be, yeah, because that's basically sort of like
What do you want to sample?
what you want to sample, right? Yeah, that would be 28 by 28. And you have like more.
Batches, yeah, you get them in batches.
Right, yeah, and that's basically what we I didn't check, but that's
Yeah.
basically what we done. Okay, and then. Where we go? So basically, if I understand correctly, that's basically would be sort of define a neuron.
Yeah.
Like start.
Exactly.
Yeah, so I'm not really sure what.
Right, so maybe for everyone, because I forgot to mention this, so. Thing is that the way people, so because, okay, you have XT and T, right? So XT is, let's say, an image, right? With whatever number of pixels you have, and that T is a number. So how do I ingest both, right? So how do I pass both to my neural network? So there's different ways in which you could do that, but actually the most popular one is something that sounds a bit silly, but what you do is basically you pass T to another neural network and maybe some embeddings, but let's not worry about that. You pass them to a neural network and you make the shape the same as the image. Like if the image has 3 channels or whatever number of channels you want, right? In our case, it has 1 channel because it's black and white, but it could have more, right? It could have any number of channels. So you'll make this have the same dimensions as the number of channels, like say 1 or 3 or whatever it is, so 64 if you have 64. And then you just pixel-wise add them up. So you will add the same values to all the pixels. So it's a way of saying, like, for instance, if you are at low times, like time equal 0.1, you're adding a small value to all your pixels. If T is close to 1, you're adding a large value to all your pixels. So the image the neural network gets look different depending on the time as well.
That would be
That's an excellent question. Yeah, well, the problem is that whatever architecture you're using, so here we're going to be using a multi-layer perceptron, like same as last time, right? A fully connected neural network. We're going to use that first. But later we will use a convolutional neural network that works with images. So then it's unclear how you would actually just condition it on a number as well, because it's a filter that goes through the image, right? So how do I put this in? So it's just a hack to pass it on to the same architecture that we've been using, right?
So I think the default operation in this workbook is to append,
Okay.
yeah, so,
For the MLP, for the multi-layer perceptron.
okay,
Because for the multi-layer perceptron, we're flattening the image, right? And
Yeah.
treating it as an array of numbers, right? We're not actually taking advantage of this spatial structure, which a convolutional neural network would do. We're just making the problem simpler, right? And then you can just append time, right? So this will be time and this will be the image, right? So for our particular architecture, it doesn't matter what you do. You can append or add. Same here, you could sum them up or you could concatenate it as an extra channel. That's also an option. It turns out it works similarly, like it doesn't matter. So memory-wise, it's simpler to just sum them up. But it's more of a trick. But for now, yeah, we will concatenate them because we're flattening things. But if you weren't flattening things, you need to find a way to insert time into your architecture. Because the velocity model needs to know both about the image and about what time it is.
But are the images the final images which you would like to reproduce?
Well,
and so
actually, what you're inputting, if you remember, the input to the velocity model is x of t. So it's the solution of this interpolation. So it's not quite x1,
It's not quite X naught, it's something in between, depending on time. Right, so this is what the model gets, X of t at a given time. So your velocity model is a function of X of t and t. So X1 is your image. So you sample a random time to solve this expectation value. Let's say we sample 0.1. Now we will take our image and a random sample and fill in 0.1 here and get something in between. And the velocity model will get that and the time. You need to know the time because otherwise there will be a degeneracy between maybe you have a noisy image or maybe you added noise. So you need to know time, right? So that you can break that problem. So what was in that part of the problem
Yeah.
is adding this velocity,
Oh, I see.
time
Okay.
stuff, but don't worry about this for now. So you see some concatenation, don't worry about it.
Just do about that because I guess
Sure, sure.
So, I mean, basically, I understand the flattening. Like the flattening and yeah, but I think don't they actually have like there was 64?
Yeah.
That you have 64 rays which are 28 by 28 long.
That's right.
And then you basically add time.
Yeah.
And but those would be the images which you would have controlled.
Yes.
So that's why I wasn't quite sure why would you just put time t for add and the one to every one or every other.
Oh, no, but during training time, you need to sample time as well. But the loss function is an average over time as well. So it's an expectation value over time.
Right.
And if you remember at sampling time, what we want to do is start from v of t at x naught and then move on, right? So you need to be able to evaluate your velocity model at different times. So even though you have your images at time 1, we're going to create another data set at different times using our interpolate, right?
Okay, that's okay.
So that's what's happening.
So that's what.
So here, well, here first you're working on the velocity model, right? So you're just making sure that if I give you xt and t, you can return the value of the velocity.
Okay.
So this is what you have to do here.
Yeah. So you basically email all the products for the that are provided for the velocity model.
Well, we're going to have some random ones up first, and then we'll learn them. So here they're going to be random first. So,
And those are weird.
right, so we're going to define them like that. So it's going to be a multi-layer perceptron, right? So this is, so you see the multi-layer perceptron takes x and time.
Yeah.
So flattening it, right?
Yeah. Sure.
And then concatenating the time.
Then basically that's pretty slow.
Exactly.
But I'm not exactly sure what actually that's.
Right, I think this is from the branch of the solutions, right?
Yeah, basically I copied them because I would never add.
Sure.
Right.
Maybe I left it.
No, actually, yeah, because I would never add. So,
Right, so before, if you remember, we had our flattened array and we were returning the probability of it being a certain number. So we were returning 10 numbers, right? So we had 10 possible numbers.
Right, exactly.
So it's probability of being a 1, probability of being a 2, right? So now we want to return a velocity value for each pixel. So we want to know how does each pixel need to move.
Yeah.
So what is the shape of the output that we need?
Right. Yes, basically the same. So we have the same input and output. Right?
Exactly,
Yeah.
same dimensionality.
Yeah.
Right.
Right.
So we want to go from 28, 28,
20. Yeah. Exactly.
Okay.
Right.
Before we were going from 28, 28 to 10 in the discriminative problem.
Right. Okay.
Now we're
yeah.
going from 28, 28.
Because we wanted to identify the number in that. Okay.
Exactly.
Right.
So this is what's happening here, right?
Ah.
It's taking the x, well, concatenating time,
Mhm.
and then It's processing it with linear layers and adding non-linearities. But at the end, it's returning something of the same shape as your input.
And that means that those would basically be the layers of the neural network, and then
They're used to fit.
but you need the same size basically to propagate from, let's say, from 28 by 28 to 28. Okay. It's that one. And then so that yeah, then basically you find the velocity model. And so how many parameters does the velocity model have?
Right, so if we, so here your initial.
Yeah, no, first of all, yeah.
So here's where you initialize the parameters, right? So you're giving it a random key.
Yeah.
To very random numbers, right? And you're initializing them. This is how you initialize the code.
Yeah, you put all at once.
Well. This is all once, yeah, because for the multi, so this is a generic model, let's say. But it doesn't know what the input shape is, right? So it doesn't know how many free parameters there are again. This is a boilerplate architecture. But now we're giving it an example input to all ones with the right shape, so that we can get a random set. And then this, if you look at params, these are the three parameters.
Okay.
So there's a dictionary, right? If you remember, it had like dense layers with kernels that were the weights and biases.
Okay.
So you
Oh, so
look at-
weight and the biases, those would be the parameters for the.
Right. For instance, we can say something like. Unuseful outcome. So, these are our parameters. Okay, so let's go into. Um. So they can shape. Have 8 22, so you're taking your images, flatten, and turning them into something that's 24.
Mhm.
And we can sum them all out. So if we go through all the layers, so this is only the first layer, but
Yeah.
go through all of them. Unless it's one. Right, so these are all the layers, right? Nine
Okay, and then that would be the 28 by 28 you start with.
plus time. Right.
Plus time for each.
Yes, for each image, it would
Yeah.
have 784, which is 28
Yeah.
28,
Plus.
plus some embedding requirements. It's not time exactly, it's not just one, but we put a function on.
Right, okay.
Making it bigger.
Right, okay. And then that goes into the first layer of the neural network, and then basically this goes from through all the layers, yeah. And then it ends up the 28 by 28. Yeah, okay.
Yes, yes. Cheers. Thanks.
Excellent.
Does everything make sense so far?
Very confusing. I'm learning.
Yeah, that's good. Not only
Lots
the
lower than the model. I must have logged in as my mom, so.
Oh.
Maybe then. Thanks. I'm looking. That's cool. I'm learning.
So it explains, right?
Yeah,
Step by step.
it's very, it's nicely laid out. It's getting better.
The loss going up.
Yeah, I think. Scroll down, so just looking at.
Oh, the images that it's generating.
Hmm. Back to the drawing board.
I mean, it's not terrible, right? You can see shapes that look like numbers. If you squint.
You can.
The definitely don't look random, right? They have some patterns, so that's a lot. Right, so it just looks like them all got stuck, right? Like,
Okay. Just literally when the model gets like, all right, I'll keep playing around.
I can show you a fun example.
Yeah, I mean, I definitely saw some. After step, I mean, the first step. I thought looked. The best.
Yeah, I'll show you an example of how the loss can be very confusing. Which generative models in particular. So if you look at this model, this is a model I trained, right? This is a training loss. Looks terrible, right? Like, I don't know, is this going down? I'm clear.
From the first steps, it does look like it, but then it plateaued.
But it plateaued for a really long time, right? It looks like it plateaued very quickly. But if you track other metrics of, so this is generating images, right? So what is the initial problem? Okay, so let's have a look at this. So this is what it was doing at first, right? This was the true initial conditions, and this is the ones it was sampling. Rubbish, right? Then it's starting to get better, looks more high resolution, right? So this is a function of training time. It's looking better and better, right? So the model is improving for sure. And we track other metrics. So this is another metric I'm tracking. This metric you can see clearly go up.
Okay, what's that?
So this is a cross correlation between the true image and the sample image.
Oh, okay.
So here you can clearly see it going up, right? But the training loss didn't look like anything like that. the completely plateau, right? And this is because the variance of this tomato is very high, because you're only averaging over a few times, right? So if all your images happen to be sampled near your noises, like your X naught, models might have high variance, right? So this loss function has very high variance, but still the model is actually learning really well. So it's important to always track more than one metric because otherwise, yeah, it would stop the model, right? But you could actually get much better. So don't trust the loss.
Okay, but I trust my eyes.
Yeah,
Pretty
yeah.
good.
So that's why this function to generate samples as you train, right? Because then you can actually see whether it's actually
Right,
moving.
right.
But ideally, you want to translate that into a metric, right? Okay, what are your eyes seeing?
Yes, yeah.
So in your own problems, you want to think about what is the right metric to track beyond the loss. That will allow you to sample
Right.
this.
Right. And the cross correlation certainly makes a lot more sense. That's much more intuitive for what I think I'm seeing here.
Right. For instance, if you had trained a classifier on numbers, you could see whether the classifier is right or wrong, right? Things like that.
Yeah, no, that's. Right, so you would apply what I didn't do, which is the
Right.
previous lesson
So you can apply
to
to
this to see how, oh, that's good.
Mhm.
And can you set up a loop with that? I mean, you can classify and then feed the results back into the generators. I mean, how does
You
that work?
could.
Did you actually improve the model basically?
Well, I would use it more as a metric to decide when to stop training. So to see if the classifier is getting bad after time, right? And then see, okay, actually that would be good here. Because the loss is not helpful. The loss might look like it's plateaued, but it's actually improving a lot still. So how do you decide when to stop?
Right.
But this is with a fully connected neural network, right? Where you have, it's a multi-layer. So I don't think I got really good images from a multi-layer perceptron either. Like, I think maybe that's as good. So that's why the next part is
So you
using.
use the convolution. But okay, I don't have a GPU, but you can do it through
Yeah, with Colab, you can,
Okay,
yeah,
okay.
without Colab, you'd be here for a long time before you see any images.
Okay, cool.
But yeah, if you don't get beautiful numbers with a multi-layer perceptron, that's expected. I don't think I do that either, so.
Subscribed. Small. So you read a book or something? Seems like you're collating some nice material or something useful.
Maybe a blog post. A blog.
Yeah, maybe that makes more sense because by the time you get to propose, everything's gonna be.
Exactly. I
It
think
has to be a living document.
it has to be living, yeah,
Mm.
I think that's true. Yeah, I also looked at course on like simulation-based inference. I also felt like there's only like one nice review about simulation-based inference, but it's so outdated already that it's like not really that helpful for students that want to start, right? Like It's a shame.
No, a bond makes sense. Or a website, almost like, you know, something where, but it's really just focused on these ones, maybe such a thing exists. And
Not really. I think like online lecture notes would make a lot of sense. So that, no.
you know, a repository.
Yeah.
Other than somebody slapped page.
Yes. Yeah, I think that would be great.
Yeah, that would be a really good thing to do, and it would take a lot of work maintaining it because it's every day.
Well, my hope is that one day I'll be teaching a class on that, and then I'll be very happy to. But once it's part of my job, I'll be very happy to do it. But for now, it's like, yeah, I would like to do it, but.
Well, I'd be, I mean, this is probably overpromising in today's world, but it seems like it would be the sort of thing for which getting support would be a no-brainer.
Right, you
Right,
think,
where you could get someone to, you know, work with you part-time or whatever to help maintain it. So
Right.
you could focus on the content and strategic vision, but someone could actually.
Right.
Yeah, outward those things.
Yeah, that'd be great. Oh, I don't know, I like doing those things as well, but I wouldn't mind. But yeah, I think right now it's also like a philosophical thing that is not part of my job. So I feel like, I don't know, I shouldn't be doing that if it's
Right.
not part of my job.
That's it.
So
That's not.
I would like it to be, but it's not. So
But it could be, and as I said, you could get support of
That's
doing
true.
that, which would compensate.
Yeah.
The time you spend doing that as opposed to you know, all the other elements of the job.
right.
And I think that's. I think that's definitely would be so helpful.
I think especially for students, right? I think it's very confusing to just start navigating all this like different models. Why are they so different? They seem completely different, but they don't see all the similarities.
Well, also just a sense of what type of model is appropriate,
Mhm.
what type of use case.
Yeah. Yeah, and in science we care about very particular things, like this molecules problem, right? Where yeah, you want it, the effects to be invariant to certain things. Most ML courses won't talk about that, right? Because they don't care.
But it's physics informed stuff.
Yes.
Just seems like. It's an important thing to consider for many applications, not all, obviously, just care about it. It's quite physical.
Right.
Sir, I have to go now because there's a lunch talk at noon, so I have to listen. Thanks. Yeah, thank you so much for visiting and giving great workshops.
Thank you.
Yeah.
It's, I know this feeling just a lot of number. And people you're adding to this.
Right.
And there's so many, this is really just additional modes and really atypical modes compared to, I mean, people don't. I haven't seen a lot of spectral. Things like that, but combining spectral series with images with text.
Yeah.
I think, or supplemented detection, or, you know, any kind of. Something like you're doing, it's just, and I don't, I mean, that seems pretty. My feeling is that, my sense is that I'm too more.
Yeah, well, I mean, you can argue that DALL-E is a multiple problem, right? Like text and images. I think with text, people have been doing a lot in the ML community, right?
Right.
Imaging text.
Right. Yeah, I guess I was thinking of. Adding
More
other types of.
Yeah, I think it-
Messenger.
In medical domains, people have also been doing this, right?
That makes
Because you have like
To make a
MRI.
diagnosis, you have this, that, and the other kind of measurement.
Yeah, and there they have loads of analysis. So yeah, there is a lot. I think in climate and weather as well, because again, they might have spectrum, different measurements. But yeah, it's more scientific domains, which yeah, than natural world.
Yeah, they're really big sets.
don't really differentiate those with the dimensionality and the weird ways in which it's sparse.
Right. Yes. Right. But lower impact as well, right? Like you work on, like so many people now, ML are working on like web development. So we have to use it. Yeah, very clear that we have to do that for sure. Whereas something Astro is like, yeah, it's a nice data set, but people are like,
Yeah, no, I think that's, my own scramble. So this discussion. How do we get how do you leverage the trillions of dollars that are being spent? Get people interested in our problems and our data. And I do think you're right, you have to show somehow helping with our problems to something they care about.
Yeah.
Or can make them money or be very visible.
yeah. Like something we've done in the past, for instance, is to present more benchmark type data sets where there's a very particular feature that is not common. Like for instance, in cosmology, it's like long range correlations and huge point clouds. So that's actually rare. Like in point clouds, people work with like shapes, for instance, right? Like a plane, and points are representing the shape of the plane, or molecules where you have maybe 20 atoms, not a big number. But point clouds where you have a large number and very long range correlations, and you can have open data sets, are rare. Like social networks are an example as well, right? But those are very, yeah. So developing these sets that can be, and showing evals that tell you whether the model is working or not, for like this long range correlation.
Yeah,
And where symmetry is so important, so you can do things like that. But I think ultimately, do we want people from ML to work in astrophysics? I don't want that. I want astrophysicists that also work on ML, like hybrids.
No, I think that's fine. I think I was thinking more just politically right now in terms of getting support.
Yeah.
For the work. If we really take the darkest scenario where half the funding goes away, you know, it's not like industry's gonna make that up, but you'd have to look more seriously at foundations. You'd have to look more seriously at industry partnerships or national lab partnerships, provided they're still non-existent.
Yes.
And so,
For sure.
you know, what is that? So what are the common interests that are translatable to other domains people would care about?
Yes, for sure, sure. Yeah.
So that's why, I mean, it's we're discussing a very interesting literature search because I feel that that's applicable in many domains.
Yes.
I think you can benefit us tremendously and have an open and relatively small set. Yeah.
I should get going myself. Thank you so much for providing with these workshops. I work in high energy experimental as a graduate student over the physics department, and unfortunately, I never really got a chance to work too deeply on the applications of neural networks in our field. So, having a chance to learn a little bit more about machine learning has been a great opportunity. Thank you.
Thank you. Sorry, what's your name?
Nicholas Lopez Canales.
Very nice to meet you.
Nice to meet
for
you.
coming.
Yeah, thank you. By the way, so one thing that confused me about your initial lecture was, so you pointed out that an issue with the data set issue in cosmology is that there is basically only one universe.
Yeah.
So you're saying that in order to apply neural networks to cosmological problems, you're dependent on the validity of simulations?
For most cases, yes. Yes. Or you have to find ways of making interesting statements, even though you know your simulations are not perfect.
Like taking a lot of systematical errors into account, basically.
Right. So yeah, usually you try to full model the systematics, but obviously there's things we don't know are there, right? So that's like, how do we then detect the fact that they're missing? It's an interesting problem as well. So you assume you have simulations and observations. How do you find what they have in common and what they're missing?
Look for the overlap there.
Yeah, yeah. But yeah, you usually rely on simulations too much.
Interesting. Well, thank you again.
Cheers. Good luck.
So much fun. This is for me, it's been great, and I know there's a lot of good feedback from the response.
Yeah, I feel like I lost lots of people, like in the first section, we were loads of people and then.
It's right now, so the term is at this juncture.
Right.
And so, and our graduate students have all their stuff due and everything, so I think we're fortunate, it's fun, people near the money. So I'm sorry that, but I don't think it was from a lack of.
Right, they didn't get scared. Well, I was worried.
I don't think they got
scared.
Or if they did get scared, they can, you know, they saw it as a challenge.
Only the brave ones came back.
Yeah, thanks very much, I mean, for doing this, I mean, that was very, very helpful. I mean, I didn't know anything about that stuff at all.
Yeah.
So now I got really interested in it. That's why I asked so many questions, sorry about that.
No, but,
Oh, they were
Thank you
really
for your
good for
question.
me, I'm really glad you asked those questions.
That's good.
Yeah.
so what do you work on?
I'm actually working on theoretical GR.
Uh-huh.
So, yeah, so I'm actually not doing a lot of things, mostly trying to do analytic calculations, so that's why as far removed from machine learning as.
That's interesting.
Right, yeah, but I mean, it's really very. Yeah, and I'm taking, I'm now actually a graduate student, and I'm taking the course here.
Oh, nice.
Yeah.
That's great. It's good. Yeah, I think a lot of people, like theorists, are getting very interested in like the theory of learning, right? So how do these models actually work? How can I learn in mapping between a normal distribution and a data distribution and sample anything?
Right,
Like,
exactly.
how is this even
Yeah.
possible? Right?
Right, yeah.
And the
then,
training
I mean,
dynamics.
Yeah, and then all the models, I mean, in a way, they have like just one underpinning, like sort of like the velocity model, like
Yes.
in a way. Well, we several times talked about Jacobian, and I mean, as a GR, you always do.
Yeah,
One
exactly.
transformations, and yeah. So I mean, so basically, when you present that sort of, you know, bits and pieces, but I didn't know anything about machine learning, and you really sort of like to. I mean, that doesn't really mean that I understand it now, but I mean, it's much better and.
Good place to start.
Exactly, yeah. It's to start on that. That's exactly what it is. Yeah. So thanks very much for doing this.
Thank you.
Really appreciate
There's so sometimes I don't know what's going on in physics right now, but our department offers a machine learning, at least applied to astronomical questions, which
Right.
definitely overlaps with interests. Shelley Fawn usually teaches that, but he's on sabbatical this year, so I maybe offer. I don't know if you can follow this spring, I'm
Right.
not sure. And then CK Chung,
Yeah.
and the department he runs, or he actually facilitates, because a lot of our graduate students run hackathons and workshops.
Right, yeah, I know.
Have you attended?
I know CK because I mean, when I started working, I originally started working with Demetrius.
Oh, yes, so
Yeah.
did I.
Yeah,
Well, I didn't start with him, I
Right.
collaborated with him,
Yeah,
yes.
okay.
Yeah.
Yeah.
Yeah, so yeah, we miss him, but yeah, so he worked with him to adapt his code basically to do first principles modeling of total destruction events.
Oh.
For the X-ray mission, the time involving X-ray mission, to try to get some constraints on mass and spin
Right.
for this mass.
Yeah,
black
exactly.
holes. And so I had a brilliant student who came and visited, and then I kept him as a postdoc. He was so great, Sixang Wen, and he worked very hard on that project. And there's a lot of interesting potential data, but there are also a lot of really simplistic assumptions that we had to use, and maybe we should talk at some point.
Yes.
We had to assume that the first of all, that the orbit circulates very quickly, but I think that may be borne out by models, but unfortunately the accretion disk is perpendicular to the spin axis. We haven't gotten to any kind of precession or stuff, even though the data seems to suggest it. So I'd like to explore.
That's great.
Yeah.
Are you based here in Slough?
Yes, I'm a professor here. That man's out of so nice.
Yeah, very nice.
It's nice you came all the way over here.